So we've talked a lot about polygons, but we haven't actually defined what a polygon is yet. Let me do that right now. A polygon is a geometric primitive that is made up from any number of straight lines or edges. The basic elements of a polygon are the lines from which it's formed and the points at the ends of those lines. These are more commonly referred to as edges for the lines, and the ends of the lines are known as vertices. Usually, a polygon is made up of the Greek derived name for its number of edges, plus the postfix gon. So, a single edged polygon is called a monogon. Two edges gives us a digon. Three edges, a trigon, or it's more commonly called a triangle. Four edges is a tetragon, also more commonly known as a square, rectangle, quad, and so on. Five sides gives us a pentagon, six a hexagon, and so on. Now, the monogon and the digon that I just mentioned aren't particularly useful to us when we're modeling. A monogon is made up of one edge, and a digon has two edges, and they don't actually enclose any space. Now, polygons are used to build up three-dimensional objects, and polygons are pretty much always two-dimensional objects, and a monogon and a digon, they're both basically one-dimensional objects, so they can't be used to actually build three-dimensional objects. So what we're interested in is any polygon that has three or more edges. In other words, a triangle or a quad, and so on and so forth. And the most commonly used polygons in 3D software are the three-edged and four-edged varieties. The three-edged polygons we know more commonly as the triangle, and in 3D modeling it's often referred to as a tri for short, so tri polygons. The four-edged polygon we know as a square or an oblong or rhombus, rhomboid, or a trapezia. But in CG circles, it's more commonly referred to as a quad. You don't generally hear them referred to as being square polygons because very often a four-sided polygon isn't actually square, and it's not oblong, it's not rhombus, or it's not a rhomboid. It's none of those mathematically defined square polygons, or rather, I should say, four-sided polygons, but it is always made up of four sides. So we call it a quad. Now, the tri is the most important polygon in current 3D software systems. A tri is the first polygon whose edges bound a closed two-dimensional interior space. This interior space is always a two-dimensional plane. This is not always the case of a quad polygon because in a quad polygon, some of the edges may actually lie out of that plane. And this is true of any polygon with four or more edges. Also, all other polygons with more than three edges can be made up by combining a number of triangular polygons. For instance, a quad polygon can be made up of two tris, whilst a pentagon can be formed from three tris. A hexagon can be formed from four tris, and so on and so forth. So the triangle is the most basic straight-edged 2D surface, and all other polygons can be approximated using a collection of tripolygons. The reason that triangles are so key to the 3D graphics world is twofold. Firstly, the surface normal of a triangle is very easy to find using a well-known mathematical formula. Now, the surface normal is the angle which points at a perpendicular angle to the actual plane of the triangle itself. So this is quite easy to visualize. If you hold out your hand in front of you and you get your index finger and you point it directly into your hand, that can be thought of as a surface normal, except that the surface normal points the opposite direction to the way that your finger is pointing into the palm of your hand. It's basically a line that points directly out of the surface, and it's used in a number of places in 3D software to work out a number of different things. And as I said, there's a well-known mathematical formula that can be used to work out the surface normal for any shape, and this formula needs any two edges of the polygon to lie on a plane. And the only polygon where this is guaranteed to be the case is the tripolygon. So if you have a tripolygon, you can always work out the surface normal for that polygon. You can't always do so for a quad polygon because in a quad polygon, some of the edges may actually lie out of a two-dimensional plane. So it's not ideal for working out a surface normal. This normal is key in working out how much illumination is taken on by that triangle when it's hit by any given light source. It's a simple case of getting the normal of that face and comparing the angle of that normal to the light's angle of illumination, and then using a proportion of that light's illumination based on the two angles' relationship to each other. If the two angles point at each other, directly at each other, that means that 100% of the light hits that triangle and is fully illuminated. If it's at 90 degrees, then there's zero illumination. The light actually goes along the edge of that face and doesn't illuminate it whatsoever. And you can use a very simple formula to work out how much illumination that face receives at any one time based on that relationship. The second point, and even more convenient, is the fact that pretty much any two or three-dimensional surface can be approximated by using a number of triangles in a lattice. We call these polygonal lattices a mesh or a polygonal mesh. Using triangles alone, it's a relatively simple task to approximate a plane, a cylinder, a sphere, or pretty much any other two-dimensional or three-dimensional object. In fact, if you look at these objects that we have here in the viewport, you can see that they're all basically made up from triangles. You can see a number of triangles making up this object here. This sphere is actually built up from a large number of triangles in a lattice. This pyramid, you can see it's got 4 triangles around the top, and it's got another 4 on the base. Here we have what's called a geodesic dome, and that's made up of purely from triangles in a triangular mesh. Same thing for this torus, this tube, this teapot, and so on. Basically, they're all made up from triangles. On planar surfaces, the number of triangles needed is often very small. All that has to be matched is the boundary of that surface. So on 2D planes with linear edges, a very small amount of triangles are needed to describe that surface accurately. However, on a 3D surface, or on a 2D surface with a very complex or curved boundary, the more triangles that you use, the finer the mesh, and the more accurate an approximation that you reach. If we look at these various objects here, these 3 objects are actually 2-dimensional planes, and this object is actually part of a sphere, and I've simplified the tessellation of it at the moment just to show you the point that I'm trying to make. As I said, these are mostly 2-dimensional planes. This is a very simple plane. As you can see, it's a pentagon, I think, here. It's made up of 5 sides. If I click on it and I turn on this modifier here, you can see it's added some mesh to it, and it's actually converted it into some polygons. If I turn on shaded view, you can actually see this area is now filled in, and it's actually made up from 3 triangles. So you can see 3 triangles there. So a very simple approximation. If I turn on the same kind of modifier here for this object, you can see it's made up of a lot more triangles. I mean, it's vastly increased over this object. And all of these triangles are needed to try and produce a reasonable approximation of this boundary that you can see going all the way around here. So as you can see, the amount of tessellation, which is basically the amount of polygons that you need to approximate a surface, changes wildly depending on what that surface is. If we look at this surface here, which is a circle, a 2-dimensional ring, we turn on Edit Mesh. Again, we've got quite a lot of triangles, although it's interesting that you can see it's a lot less than on this surface over here. But again, a lot of triangles are needed to approximate this surface. If we look at this object, which is effectively a 3-dimensional ring, in other words, a sphere, if we start increasing the segmentation of this, we want to try and approximate this kind of boundary here. But this is also a curved object. It's in 3-dimensional space. So let's just try putting up the tessellation. And you can see we're getting a bit of an approximation of a circle here. But you can see that the approximation of the curve in this dimension isn't very good at all. So let's try and to increase the tessellation until we start to get a better approximation. Now you can see we're getting something that's approximating the curve. But again, it's not particularly great. So we'll just keep on increasing the tessellation until we get a reasonable approximation. So you can see that from the side, we're getting a reasonable approximation of this curve. And also from this direction, you can see also we're getting a reasonable approximation also. This object appears to be made up of mostly quads, but it's actually made up of tries. So if I just add on an edit mesh modifier here, select all the edges in the object, and then make them all visible. Because this is an edit mesh, it's all made up of tries. So you can see there are a lot of triangles that actually make up this object when you compare it to this circle here or these shapes over here. So three-dimensional curved surfaces use a lot more polygons than 2D planes, and curved edged 2D planes use up a lot more polygons than linear edged 2D planes. So this is something worth bearing in mind while you're modeling. So as we've just seen, the try gives us a simple primitive which is perfect for use in 3D graphics. You can work out the surface illumination using a try, and even better, as a primitive, it can be used to build any complex two-dimensional or three-dimensional surface. And the quality of that approximation is also totally flexible. In the early days of computer graphics, the ability of the triangle to define any geometric primitive with a small and even better controllable memory footprint was vital. The beauty was that you could then take those same tries and you could then shade that surface with a minimum of fuss and computational power. So the triangular polygon really was a wonderful fit for the task defined by those pioneering software engineers. In those days, memory and computational power was at a premium. Today, we're all basically working with supercomputers. But in those days, even though we're very, very expensive pieces of hardware, in comparison to modern hardware, they were very, very basic. Today, this need for super efficiency is still with us. Of course, our memory limits have gone up from, say, 32K or 64K, 128K to 4 or more gigabytes. It's just a massive, massive increase. And our CPUs are thousands of times faster as well than those early PCs or mainframes. But still, the same rule applies. If you keep your modeling and rendering pipeline as simple and efficient as possible, your computer will be able to store more complex models and render those models as quickly as possible. And for this reason, the try is still the keystone of most computer systems rendering and modeling systems. And that goes for both pre-rendered images, the kind of images that you see in movies and in videos and in TV. And it also goes for real-time rendering systems, the kind of systems that you see in modern video games, games consoles, and so on.